Hey there, fellow knowledge seekers. Have you ever wondered how computers store and organize the massive amounts of information we throw at them every day? Well, the answer lies in the fascinating world of data structures. Think of data structures as the ingenious containers and organizers of the digital world. Just like we use different containers to store leftovers, clothes or tools, computers use data structures to store different types of data in a way that makes it easy to access and use. These structures are the unsung heroes of every app, program and website you use. Data structures are the foundation of efficient programming. They provide a way to manage and manipulate data effectively. Understanding data structures is crucial for designing fast, scalable and optimized software. Whether you're browsing the internet, playing video games, or simply sending a text message, data structures are working behind the scenes, making sure everything runs smoothly. Let's start with one of the simplest and most fundamental data structures, the array. Imagine a row of mailboxes, each with a unique number. That's an array. Each mailbox represents a memory location, and the number is its address. Arrays store elements of the same data type in contiguous memory locations. This means that the elements are stored right next to each other, making it very fast to access any element using its index, which is like the mailbox number. For example, if you want to store the ages of 5 students, you can use an array of integers. Each element in the array will represent the age of one student. Arrays are like well-organized shelves. They provide a structured way to store and retrieve data, making them essential for countless programming tasks. Now, imagine a chain of paperclips, each linked to the next. That's a linked list. Each paperclip represents a node which contains data and a link to the next node in the chain. Unlike arrays, linked lists don't require contiguous memory locations. Nodes can be scattered throughout memory, connected by their links. This flexibility makes linked lists efficient for tasks like inserting or deleting elements in the middle of a sequence. Think of a train, where each car is connected to the one in front and behind it. You can easily add or remove cars without affecting the entire train. Linked lists are versatile and play a vital role in many applications, including memory management and implementing more complex data structures. Let's head to a theme park to understand stacks and queues. Imagine a stack of plates. You can only add or remove plates from the top, right? That's the last in, first out, LIFO principle of a stack. Now think about the line for a roller coaster. People join at the back and ride in the order they joined. That's a queue following the first in, first out, FIFO principle. Stacks and queues are abstract data types that define the order in which elements are accessed. Stacks are used in undo-redo functionality, function call management, and more. Queues are essential for task scheduling, handling requests in order, and other applications. These structures are like real-life lines, managing the flow of data in different ways depending on the task at hand. Section 5. Trees, family trees and file systems. Remember those family trees we used to make? They're a great way to understand the concept of tree data structures. In computer science, trees are hierarchical structures with a root node at the top and branches connecting nodes. Each node in a tree can have child nodes, forming a parent-child relationship. This hierarchical structure makes trees ideal for representing relationships, organizing data, and enabling efficient searching and sorting algorithms. For example, your computer's file system is organized as a tree. The root directory is at the top, containing folders or subdirectories that can have files or more folders inside them. Trees are like organizational charts for data, providing a structured way to represent and navigate hierarchical relationships. Section 6. Hash tables, instant retrieval. Have you ever wondered how dictionaries provide almost instant definitions? The answer is hash tables. Imagine a magical dictionary where you provide a word and it instantly flips to the correct page. Hash tables use a hash function to calculate a unique index for each key, allowing for quick data retrieval. This makes them incredibly efficient for tasks like searching, inserting, and deleting data. Think of a hash table as a well-organized coat check. You give your coat or data and receive a unique tag or index. When you return the tag, the attendant can quickly retrieve your coat. Hash tables are like data retrieval ninjas, providing lightning-fast access to information. Section 7, Graphs, Mapping Relationships. From social networks to maps and recommendations, graphs are everywhere. Imagine a network of dots connected by lines. That's a graph, a versatile data structure that represents relationships between entities. Each dot is a node or vertex, and each line is an edge, representing a connection between nodes. Graphs can model anything from friendships on social media to connections in a transportation network. Think of a map where cities are nodes and roads are edges connecting them. Graphs are used in GPS navigation, social network analysis, recommendation systems, and countless other applications. Graphs are the cartographers of the data world, mapping the intricate connections between different pieces of information. Section 8, Choosing the right tool. Selecting data structures. With so many data structures available, choosing the right one is like picking the best tool for a job. There's no one-size-fits-all solution, and the best choice depends on the specific task and the type of data you're working with. When selecting a data structure, consider factors like the type of data, the operations you'll be performing, and the efficiency requirements. For example, if you need to maintain the order of elements, a queue might be suitable. If you need fast search and retrieval, a hash table could be the answer. Each data structure has its strengths and weaknesses, and understanding these trade-offs is crucial for making informed decisions. Section 9, Real-world applications, data structures in action. Data structures are the hidden heroes powering countless applications we use every day. From the moment you unlock your phone to the time you stream your favorite show, data structures are working tirelessly behind the scenes. Here are just a few examples. Social media graphs are used to represent social connections, recommend friends, and deliver targeted content. Search engines, hash tables, and trees power lightning-fast search results and indexing of web pages. Navigation apps, graphs, and algorithms like Dijkstra's algorithm help find the shortest routes between locations. Operating systems, stacks manage function calls, queues handle process scheduling, and trees organize file systems. Understanding how data structures are applied in the real world provides valuable insights into the design and functionality of the technology we rely on. Section 10, Performance Matters, Time and Space Complexity. Imagine searching for a specific grain of sand on a beach versus finding a book in a library. The latter is much faster because libraries organize books for efficient retrieval. Similarly, the way we structure data significantly impacts the performance of algorithms and software. Time complexity measures how the execution time of an algorithm increases with input size. Space complexity refers to the amount of memory used by an algorithm. Choosing the right data structure and algorithm can mean the difference between a snappy application and one that lags or crashes. Understanding performance considerations is crucial for writing efficient and scalable code. Section 11, The Future of Data Structures. As technology advances, so too do the challenges and opportunities in data storage and processing. With the rise of big data, artificial intelligence, and the Internet of Things, data structures continue to evolve to meet the demands of these fields. New data structures are being developed to handle massive data sets, support complex queries, and enable real-time data analysis. The future holds exciting possibilities as we explore innovative ways to organize and process information in an increasingly data-driven world. From optimizing existing structures to inventing entirely new ones, the field of data structures is dynamic and constantly evolving to keep pace with technological advancements.